Hi, everyone. Good morning, good afternoon, good evening. Thanks very much for joining us at the first tinyML Auto Machine Learning Forum. I really appreciate you joining us, and I hope you're looking forward to this exciting couple of hours as much as I am. We're going to really try and do our best to show you a lot of what's going on in a really dynamic industry, a really dynamic field of auto machine learning for tinyML, and see what all we can do with it. So let me get started. First we have to thank our Tiny Machine Learning strategic partners. I'm not even going to attempt to read all of the companies that are sponsors of the tinyml.org, but you'll notice that quite a few of the names on this slide are participating in today's forum, are either showing demos or are amongst our panelists. And so, it's quite a big area in overall in the work that goes on in tinyML, or, teams and groups have some part of it that they work on that's in this auto machine learning space. So we want to also remind you to, if you haven't already, if you're on here, there's a good chance you have, but make sure you join one of the growing tiny machine learning communities on Meetup and in LinkedIn. There's links and QR codes on here. There are also, you'll want to subscribe to the Tiny Machine Learning YouTube channel. We are recording today's event. This whole recording will be posted on the tinyML channel, including this video pretty soon. So subscribe, see as the stuff comes up. And as I'll mention in a little bit, we're going to have some follow-up deep dive sessions on a number of the tools we talk about in today's sessions. They'll also be recorded, posted to YouTube. And so, check back there, come back there and take a look later on. The other big event coming up soon is the Emea tinyML Emea Innovation Forum in 2022 in October in Cyprus. The call for presentations is open. You can see the link there on the screen. Go sign up, look at going. I think it'll be another really good tinyML event. Always interesting and exciting kinds of stuff. So do please take a look at joining and try and present. I also really want to take a minute and thank the Technical Program Committee. I was lucky enough to be the chair, but none of this would have come together without a bunch of people. Sam, Martin, Kate, Tomas, Danilo, Evgeny, a few other people who dropped in from time to time, who really helped put this whole event together, came up with the idea, and really put their energy and time into making it happen. And so, as I heard both Evgeny and Ira say pretty recently, if there are other areas you're really interested in for tinyML, starting one of these technical program committees and volunteering is a good way to get them going. Before we get on to our keynote speaker, I did want to point you really quickly, just as a reminder. You probably saw this page maybe in an earlier version, but on tinyml.org, we have this tinyML AutoML forum where we talked about this event. You probably went to register, but there's a couple more things on it, even very recently. First is we have this document available, which is our kind of summary of the current state of this tiny AutoML market. And all that really is a bunch of these 2-pagers or 1-pagers, summaries from each of the companies that are presenting today on what their tool can do. But we tried to do it in somewhat of a standardish way so that you could really take a look at the diversity of what's going on out there, what everyone could do, how it worked, things like that, in a pretty concise kind of way, and then have all the links to go learn more. And so that's available there. The other thing that's available, as I mentioned, is we're having follow-up sessions. So the first thing we're going to do after our keynote speaker is a series of 3-minute demos. So obviously 3-minute demos will give you a taste, but you'll not be able to really get in depth. So we have a set of 1-hour follow-up deep dive tutorials already scheduled. This isn't everyone. I think we'll probably be adding to this schedule over the next few weeks, but it's most of the companies that are presenting today. And the links are all live, so you can go and click on them and sign up for one of those deep dives right now, or as we're going through the demos or the Q&A, if you think I'd like to learn more about one or another of these tools, a great way to learn more is to go sign up for the deep dive tutorial. Do it right now before you forget, and get in there and kind of learn some more. So that's my first call to action for you, but we'll kind of remind you of that a little bit later. To again introduce how we as a working group decided to try and organize both our one-pagers, kind of what were the common things that any of these kinds of tools looking at tiny machine learning and automatic machine learning had to look at. You know, we thought about three big categories of topics. First, we're going to talk about use cases and data. You know, what are the common use cases, user use cases? What's the kind of data that people have to deal with? Second is, what's the overall process that people have to go through to get their problem solved, to get their machine learning model built, deployed, whatever it might be. And third is, what kind of productivity do these tools bring? Because that's usually the case where the value we're looking for is in things like that. So we're going to organize the questions in roughly those categories. We're going to start with use cases and data. So I will start off with our first question to Chris Rogers from tinyML. Chris, tinyML supports a wide range of sensors and IoT applications. Could you give us an interesting example of a use case tinyML AutoML engine has been used on?
Yes, from my standpoint, an interesting example is an actual real-world deployment that's solving an actual commercial problem. You know, demos are great, but what's most meaningful is when a user is deploying this to solve problems. And one of the more interesting ones that we've done involved a tier one semiconductor manufacturer who had challenges with a photonics optical networking product. Essentially, that production process had a critical step where there was an alignment of components on the board for their networking device that was an irreversible process. Either it got done right, or you had a failed, expensive scrap piece of product. And the factors that were involved were non-obvious. So there was vibration, there was environmental, even humidity played a role. So you had a lot of dissimilar sensor types that were involved in predicting whether or not you would have a successful part or a piece of junk they would have to scrap. So they did their best with heuristics to try to solve that. Really, the only thing that they were able to do was just tighten the machine tolerances to a level where they could get good results. But the tolerances were so tight that the result was that while the yield improved, the throughput time was reduced significantly because they had all this unplanned machine downtime to go and recalibrate and get it back within the constraints of the tolerance. So what we did is we worked with a partner, Adaptix, who focuses on the end piece, and we focused on the tinyML model to take a multi-sensor approach of all these environmental sensors plus motion plus vibration and create a predictive model to say, you know, before this critical irreversible step was done, can we predict a good outcome for a part or not? And the result was that they were able to loosen the tolerances and improve their throughput by double what it was. And it was successful enough that they then deployed this to 100 machines across Southeast Asia that were doing this manufacturing step for them. So that was an exciting outcome for the customer, for us, and for our partner Adaptix.
Yeah, really cool. And I think that's something we see a lot, is just the amazing breadth of different solutions that people find to apply these kinds of technologies and sensors and tinyML to. Anybody have any follow-up questions on that one? For your users' projects, can you give us a sense of what proportion use kind of the presets that are built into your Eon tuner versus their own plugins or their own customizations?
Really interesting question. Yeah. In all fairness, like 98% of people just use presets. The interesting thing actually. So I was listening to Kjell's keynote, and so AutoML is a really interesting space, but it only helps you like kind of so far, right? You first need to have this data set that actually is good, and then that already gets you 90% of the way there. And then the Automl pipeline maybe gets you like this last 9%. But this first 90% is super interesting. So when I was listening to Kjell's keynote, I realized something that I think would be super interesting for the audience. So one thing we do now is that when we generate a neural network, you generate first some input parameters, like do we need to downsample, then some signal processing parameters, like what are the right filters, what is the right FFT length, and then you generate a neural network. So one of the things we now do is that we take the embeddings from the neural network, so just before the network makes a conclusion, and then we use that as a visualization strategy. So we kind of give you the speak into what the network thought at any step. And what we can do with our Automl pipeline is actually compare that between runs. So really interesting. I threw a link in the chat window for everyone to see. But the really interesting thing there is that you can see what did the network think in each of these configurations. And that is actually much more interesting because now all of a sudden you see, hey, it got confused by this and this sample, which I think is a really interesting part of this data thing. So yeah, come back to your question, 98% is presets, 2% is custom. But I think the most important part is just get data right. And we have some cool stuff there. So
I'm going to follow on to the get data right question with a question that I think you already answered in the Q&A, but kind of talking about how to find optimize the data representation, right? And the example they used was Emil, I'll give him credit, was selecting the best sampling rate for an audio data set, given hardware and accuracy constraints. So
it's actually two things. I think actually Automl is the wrong abstraction level for that, because this is, in all fairness, it's deterministic, right? If I look at a data set, I can tell you, like, there's actually very little information about 4 kilohertz, for example, in speech. So we've been trying to decouple that a little bit. I know that some other companies in the same space, Reality AI, for example, is really good at this kind of stuff, where they say, actually, we tell you what the interesting frequency domain on this thing already is. So we try to attach it in both ways. My feeling always, this is the better you understand what you're looking at, the better the results. Like there's only so much stuff that we can kind of generate in an Automl pipeline. So we'll go through it as a thing, but we try to make it more accessible. I think a lot of people here share this, like the tinyML guys coming from a bit more traditional background and really understanding signals would go with it as well.
Yeah. Anybody else want to jump in on the how do these tools, or how do any tools help you kind of find the right input settings for your sensors?
I think I'd underline the data set one again. I mean, our customers have always had this issue that, you get it working in the lab, you get it working in a certain amount of customer sites, but then there's a corner case that you've got to cover, and covering a data set with all of those corner cases, that's the challenge for me.
I think actually just trying out different scenarios for collecting the data, taking a look at it, analyzing it, and kind of just trying to understand it goes a long way, because then you know what went wrong, what's missing, and then you can reiterate. And it's about just you do a data collection, you learn, you make mistakes and you learn from them, and then you do a bigger data collection, you find some missing data, and then you do an even bigger one. So as you learn, you can go further.
Yeah, I would agree with Sam's point. Incremental, iterative approach to data collection versus collecting everything up front only to discover that you wish you'd done something slightly different is definitely a best known method here.
Yeah, and I think you see it wider. Well, I mean, anyone is. I know we all like benchmarks and stuff, right? But if you look at, for example, what is an ML perf, which people use for performance, but also a little bit for like, hey, we can get higher accuracy, or even in common voice, like literally, like doing proper analysis on the data that's sitting in there, you'll already realize, well, the best way to get a 10% point increase on this is just clean up the data here. And you can throw a million AutoML tools at it, but they will never find that. So.
Yeah, and I mean, I think for people who might be new to the tiny machine learning space, and certainly tiny machine learning AutoML space, and are more used to the the space of big data machine learning, where you're used to large training data sets. I think a lot of us have the experience of sort of what we just mentioned, that you never have enough data or any data to start, right? You're starting with, I think half the demos we just saw, was like a couple of minutes of data that you started training with. And to make a real production model, you might collect more, but it's a very incremental strategy. And so then you do have to spend some more time with it and understand it and try and build something out there. Okay, Eric, Noda AI has some other specific use cases they've focused on. Can you describe those for us?
Noda AI, the main focus is on Nespresso, which is a AutoML platform, but as you noted, we have several other use cases, and there are two types of use cases. First one is we have industrial scenarios, and the other case is a chip level implementation. The model produced by the Nespresso was implemented in an intelligent transportation system and driver monitoring system. So we are different with other companies that we actually perform something like vertical integration. So we develop and we operate the web service, and further we implement in rare cases. So intelligent transportation system and driver monitoring system. So ITS, it's called ITS, Intelligent Transportation System, is for controlling traffic signal and to give all our people like pedestrian or drivers, and it controls the traffic lights dynamically by watching over the drivers or pedestrians. And driver monitoring system is for drivers in autonomous vehicle. So in autonomous vehicle, the drivers can easily lose attention because they don't drive while they're driving. So the small camera in a black box, and it's an edge device, the small camera in a black box watches over the driver and give alert when the driver is drowsy, like sleeping and yarning like this. The point here is we could implement a 5 to 6 object detection models simultaneously in edge device like Raspberry Pi Zero, which is a 15-box computer, very small computer. So we could run 5 to 6 models simultaneously. So it's our strong point because we could compress our model in small manner. So on the other side, on chip level, rather than an industrial level, we have collaborating with Renaissance or Halo, which has their own microprocessors. So our Nespresso enables developers to build, optimize, and deploy up to over 30 times lighter AI models on Renaissance chips, the microprocessor, which delivers over 2 or 3 times rather faster AI inference at low power consumption. So these are two types of our main use cases.
Excellent, thanks.
Do you have any more comments or
anybody? Any other follow-ups? Cool. Chirag, the AI model efficiency toolkit can be used to optimize models in a number of use cases. You talked, the video went through a little bit of that, but maybe you can describe how it achieves some of the smaller size models?
Sure, yeah. Thanks for the question. I hope you can hear me.
Yep.
Yeah, so you saw in our video presentation, right? We cover a broad gamut of use cases like classification, object detection, keyword detection, all sorts of model types, model use cases. And how we actually do that is really through quantization and compression of neural networks. For those who are a bit familiar, the quantization, typically models are trained in floating point length. But when you want to take it to tiny devices, the memory is a constraint. You want to compress down the networks. So it would be great, right? If you could take a 32-bit model, run it, compress the bits to 8-bit model for 8-bit weights to improve the memory requirements on the device, also bring a lot of energy benefits, right? So compression quantization is a big focus for us. And there are several techniques available in AI model efficiency toolkit. We have simple, easy to use techniques like post-training techniques, where your model is available to you already, it's well trained. You do some post-processing on top of it, make it more condition friendly, and then deploy to the target. At the same time, sometimes I think you heard in other presentations as well, like it's not just about compressing the network or quantizing the network. Right? We need to make sure the accuracy is maintained. You may want to do some fine tuning as well on top for more sophisticated use cases or to get to the last bit of accuracy. So we have techniques that like quantization of a training kind of techniques where you can fine tune the model and get the best performance more in terms of like the accuracy as well as the quantization, the model size reduction. Largely 32-bit to 8-bit is well known, but what Emea does is it has some state-of-the-art algorithms, more techniques where we can push the envelope further, take it down to 4 bits as well. So we can keep on seeing more and more gains, more model size reduction, energy efficiency improvements, and so forth. So on top of that, like we also support compression. So I think quantization and compression are two complementary techniques. We can do quantization plus compression as well. Like specifically, we do some sort of semi-structured compression techniques. Channel pruning is well known. We have automated ways to how do you do the channel pruning, for example, for convolution networks in best possible manner and get an optimized model out, right? And ultimately, the proof is in the pudding, how well these techniques work, and that's where like we have released a bunch of models in our model zoo. Just this week, right, or maybe last week, we released like 8 to 10 models for super resolution use case. Like very important for like obviously on the mobile side where everyone wants to get the best possible picture quality and so forth, but also for XR and a lot of other emerging use cases which will also go down make its way into tinyML kind of use cases as well. So yeah, basically it's a full package. Feel free to explore on our open source GitHub and then shout give us questions if there are any on the GitHub. We'll be happy to help.
Awesome, thanks. Any follow-up questions or comments? So I'll ask one from the Q&A, not actually to you, Chirag, but to Daniele. There's and Daniele, like Chirag, you're representing more of an open source development team rather than a commercial AutoML company. And the question from Nick is for you. Thank you for the presentation. Are there by any chance, concrete plans to integrate more sophisticated quantization methods into QKeras? And the reason I'm bringing it up now is he gives the example of Ada-round as introduced by Qualcomm. So I'll throw that one out there for the two of you to talk about.
Yeah, thanks for the question. And I'll just clarify, anything I say here is just my personal opinion. I can't speak for Google. But I will say that, yeah, QKeras has quite a few different quantizer types. So as well as the standard symmetric quantizers, where you can take a continuous value and discretize it into equal size bins, in QKeras we can also create unequal size bin. So for example, we can have more precision in part of the range and then more range on other parts, so larger bins on the outskirts of what the quantizer can represent. And this can all be trained using quantization-aware training, right? So I think it can be quite effective. Now, specifically for Ada-round and other algorithms like that, I'll have to get back to you. I need to make sure I get the details right before doing any comparisons. But I do think that we have some pretty compelling quantizers in QKeras.
Cool. And yeah, feel free to follow up on the online chat as well. But I'll ask you another question before you go do that. You've also gotten to participate in a couple of projects using QKeras and AutoQKeras Vizier for edge machine learning projects with some really interesting performance requirements. Could you share some of those examples?
Yeah, for sure. So the most interesting published work about this is when the QKeras team worked with the CERN team to create a model to detect particle collisions at the Large Hadron Collider. And so due to the nature of the research conducted there, they are collecting tens of terabytes of data per second when any collision occurs, right? And there's so much data, they need to figure out what data to keep and what not to keep. So to do this, they actually decided to create an ML model that could make this classification, right? So because of the nature of where it's at, the model had to run on the order of microseconds, right? We usually talk, milliseconds. They were looking at microsecond inference time. So they started with a baseline 14-bit high precision model and then used QKeras and AutoQKeras to compress it down to this heterogeneously quantized model consisting mostly of 4-bit, 3-bit, and binary weights. So very, very low precision. And in this context, when I say AutoQKeras, you can think of it as V0 as a more parallelizable version of AutoQKeras, but the same concept applies. So then after compressing down this model, they used a high-level synthesis technology to transform the model to run on an FPGA to get even faster inference. And their final results were they were able to achieve a latency of 55 nanoseconds, and they also reduced the resources consumed on the FPGA by a factor of 50, going from a DSP utilization of 56% to only 1%. And also, if we look at energy usage, like I showed in the demo, they were able to reduce it by 75% compared to an unoptimized quantized model. But even with all this reduction, the accuracy remained high. It only dropped 3%, which is quite good. And then all of this work was actually published on Nature Machine Intelligence, and it ended up on the front page of the website. So I definitely recommend you check out the paper. You can find it just by Googling, QKeras CERN paper, and it'll pop right up.
Very cool. Particle detection with tinyML. I like it. That's good stuff. Okay. Blair, today there are dozens of neural network frameworks available on the market. Why did you and Newton decide to create your own framework and use it on your AutoML platform?
So I guess you're kind of asking us, why did we choose to be different? And I always like to say, if you want to do the impossible, you have to do the unthinkable. And that was our approach. And part of doing the unthinkable was, how can we enable tinyML for everyone? And we meant that in a very literal sense. And when you begin to kind of take a look at what are our options for today, is really you have two options. You can either go with some existing neural network frameworks that are out there, whether it's TF Lite, whether it's PyTorch, or you can go with some non-neural network algorithms that are out there. But both of them kind of come with their own limitations, their own disadvantages. If you're so happen to be building models, manually, it's a very iterative process. It's kind of, to some degree, you're kind of hunting and pecking in the dark until you reach a model that you believe meets your business requirements. And then after that, you kind of have to go through some additional steps, whether you're going to go through quantization and pruning, which is, let's say, a topic that a lot of us are discussing today. But oftentimes you still end up either compromising accuracy, or you end up with a model size that is not meeting your requirements. And we know in today's day and age, when it comes to tinyML, real estate, that's your currency. So we wanted to be able to not only address some of the limitations that existed with those existing frameworks, where we're now building models where you don't have to perform any compression techniques. We're now building models that natively out of the box are silicon agnostic. They support 8-bit, they support 16-bit hardware out of the box. So we wanted to be able to do something that wasn't being achieved today. And then the same thing when you begin to talk about some of the non-neural network algorithms that are out there. Not only do oftentimes you, again, either end up with a very heavy footprint, but a lot of times those non-neural algorithms, they only can handle tasks that are, let's say, have very simple or limited dependencies. And if you're looking to do something in production, oftentimes that's going to come with a fair amount of complexity, whether it's PME, whether it's random forest, et cetera. So we wanted to take an approach that addressed the limitations that existed either by leveraging some of the existing frameworks that are out there, as well as addressing some of the limitations for some of the non-neural network algorithms that are out there. And that was our objective. Our objective with Newton is how can we improve upon the limitations that are out there? And that's what we look to accomplish. So we look to accomplish being able to, empower our partners, empower our customers to build models that are less than a kilobyte in size in one iteration. So in taking this approach, we don't use TensorFlow. We don't use any existing frameworks that are out there. We developed our own global optimization approach where we don't use backpropagation or any stochastic gradient descent or anything like that in order to address some of those limitations that I was originally mentioning. So right now, we're able to accomplish this with our own algorithm, where all of our models, as I mentioned, are less than a kilobyte in size. You don't have to go through quantization. You don't have to perform any compression techniques, and you don't compromise accuracy along the way. And we're able to address that, whether it's a complex task, non-complex task, whether it's audio, et cetera. And oftentimes we find that we're able to accomplish this. Our customers have an extremely small footprint, oftentimes 10, sometimes up to 100 times smaller than what they would get with some of those existing frameworks. And of course, once again, we're enabling all of our customers to be able to accomplish this irrespective of which hardware that they're using. So our goal was to really try to achieve the impossible, do something that no one else was doing. And that was our goal, that was our objective. And so far to date, that's what we've been able to accomplish.
Very cool. The audience got excited when you started talking, and you got a couple of questions that popped up all around Newton. So I'll ask you the last one because it's an entertaining question. So Ju Chan asked, I've been building models on Newton for several months, really small models, and I have all the functionality on my free subscription. What's the catch?
Well, if they've been having the opportunity to leverage our platform for a few months, then they should realize there's no catch. We do we do make our platform available, full functionality for free to all developers. If there was only one limitation, I would say is that all of our training occurs on GPUs. So it is a SaaS-based solution, is an AutoML solution, so it's cloud-based. That would be the only catch, I guess you would say.
Cool. And it looks like you have some more questions. I'll let you catch up with the other ones offline. So next we'll go to Sam Imagimob. Like many of us in the tinyML community, you focus on lots of types of time series sensor data, but you mentioned radar sensors in the demo video and in your one pager. Can you tell us more about some of those use cases with those sensors?
Thank you, Elias. Yeah, so first of all, let me talk a bit about the benefits of using a radar. So you're able to transmit the radar signals through obstacles, small obstacles, as well as such as dirt and other material, which makes it more robust than, say, a camera. And so this would allow us to do something like what we've done with these earbuds. So these are a fully functional prototype of earbuds with our tinyML in it. So it has gesture control, so you can control your music and skip songs, control the volume, and so you get functionality that you wouldn't otherwise have because you can't add buttons to such a small device. The other aspects of radar is that they don't have the privacy issues that cameras would have, and they are also able to detect signals in 3D. So you get the depth aspect, which might be valuable in some cases. So to answer your questions about the actual applications, one of the applications that we've been looking into is using fall detection. So you could have a radar set up inside of a room, monitoring the room. You don't have the privacy issues because you don't see people's faces. And then if a person falls in that room, then you can alert the relevant authorities. So you could set it up in nursing homes and help elderly to, yeah, in case they get hurt, they fall down, they have issues getting back up. Or you could have it set up in a factory, somebody gets injured or something, you can detect that, and somebody can go out there and help them out. The next thing is, next application is gesture detection, which is what I just showed with the earbuds. You could have it in these earbuds. You can have it, for example, to control music. You can have it in some kind of device on your TV, so you can you never have to try to find the remote again. You can just gesture to your TV and control it that way. You can have it in a car, so you can have smoother look and improve safety because you don't have people fiddling around with buttons or knobs or anything like that. Another use case is to using for example, something like an automower, or the case that Shell pointed out with these farming tractors, where if you have a camera, it would get dirty very easily. So using a radar would be beneficial in that regard. And you could use it to detect if you're still on the grass. If you get off the grass, then you can make sure to stop the blades or even raise them so you don't damage them. Or you can completely eliminate the need for perimeter wires. So you can just have it immediately detect when it's going outside of the grass area. Another application that we're looking into is object detection. For example, detecting people and what they are doing. For example, if a user sits in front of a laptop, you can have it automatically turning on that kind of functionality. Yeah, so that's all the use cases that we're looking into with the radar, and we're working with the Aquanair radars and Texas Instruments radar.
Awesome. Great. So that was a great answer, and a lot of different use cases. And I think all of our panelists kind of brought up lots and lots of different of these tinyML use cases that they've seen. We've seen our customers or partners or people using our toolkits kind of address in the tiny machine learning, auto machine learning, in this kind of space, from smart cities optimizing human activity recognition, particle detection, image segmentation in videos and for self-driving cars. Kind of I think there's, this is what I think a lot of us keep seeing is that, and this is a lot of the exciting part of tiny machine learning, is that there are kind of this whole new sets of possible use cases and applications being opened up by the ideas of putting these machine learning models on these little tiny devices, and being able to get them running locally on battery power, or even squeezing things down that used to have to run on servers onto smaller hardware. Sorry, I have both a Jetson and a little Arduino on my desk for completely unrelated reasons to this whole talk. So, all of those things are, kind of, and then tools that make us productive in doing that kind of work is what we're all excited about with AutoML. So that's kind of our data and use cases section of the whole thing. Does anybody else have any other wrap-up thoughts before I move on to the next? Anybody jump in? Nope. Okay. All right. So the next idea, the next topic we want to talk about a little bit is process. So this whole idea, there's always steps in our flow, right? How we go from an idea to a product. At the highest level, that's our goal. That's our customer's goal, is to go from some idea to something working in the field. Now, lots of times we as AutoML tool companies or tool development teams are only helping with certain parts of that process. So what we wanted to try and do in the one pagers about each of these tools was give some kind of a sense of which parts of the process do we help with. Are there pieces that help with the whole thing and the whole tinyML process, or subsets or things like that. So the questions in this next section are all kind of focused around that topic. How do things fit into the process? So I will start off back again to Chirag with AI Met. How would users fit it into their flow?
I think that is an interesting question, right? It was referred to in the keynote as well. If you go back, any breakthrough technologies, like the barrier to adoption is like the workflow, how well it fits in the existing workflow, right? We often hear from customers, do I need to learn a new tool, adopt a new framework? How intrusive it will be to my existing well-established workflow? So AMET paid specific attention to this, and our answer is, it's very non-intrusive. Your customers are using, say, PyTorch, TensorFlow, Keras for training their models. AMET plugs in more or less seamlessly into the existing workflow. For example, if you wanted to evaluate the performance of the network, so after your quantizing, they can simply use their existing evaluation functions that they are using. If they want to fine-tune the networks, for example, the quantization over training that I mentioned, so no change to their existing training pipeline. You continue to use your current pipeline, call some APIs. Again, there are not many, like maybe 2-3 API calls. You can call the AMET functionalities, techniques within your training pipeline, uses the existing data loaders, existing loss functions, no change really, right? And you can seamlessly integrate into your workflow. So in practice, right, what we have seen how our other customers or even the broader AI community has been using two ends of the spectrum, like typically model designers. They have the full pipeline, the data, that everything. They train the model day in and day out. They have found it easy to integrate into their workflow and get the optimized models up. On the other hand, like there are a lot of deployment teams whose goal is just, someone has given them their model, take this model, put it on your edge device, and make it run, right? So they essentially threw the ball to the other team. Even in such a case, like AMET works seamlessly. Even the deployment teams, they are not well experts in training and so forth. They can use our post-training techniques, for example, a bit more like user-friendly, get turnaround times are faster. They can use those kind of techniques as well and get the job done. So ultimately, we see it in AMET fitting into two places. One is during the design itself, stage itself, and then during the deployment phase as well. And depending on where users plug it in, the benefits and kind of advanced techniques they can use will vary. But it can fit well in both the stages of from the design to the deployment and get the best performance out.
Excellent. Thanks, Chirag.
Thank you.
Wan Yu, whoops, wrong question. Sorry. D, you're next. OmniML's product kind of changes the tinyML development process in a unique way. Can you describe it?
Yeah, I think the biggest change is that whether you're doing your optimization before your training or you're doing your optimization after your training, right? I think what we've noticed is that once you get a model, right? Once you get a model trained, and then you start optimizing it, you're already extremely limited on the optimization space, on the types of optimizations you can do. It is true that, like pruning, like quantization, and a lot of the other optimizations are extremely essential. But however, we do believe that more actually comes from designing the model itself, right? Just to take a very crude example, right? If you take an AlexNet, right? No matter how well, or a VGG, right? No matter how well you optimize it, you're never going to fit it into a tiny microcontroller or tiny devices with constraint. There is a limitation on the model itself. There's actually a lot of advance in both the industry and academia from the fundamental algorithms, like the mobile nets, right? Like the efficient nets, advancement into the model architecture, into the fundamental model algorithms itself. I think, yeah, the vision that OmniML have is that we need to look at this layer, like in the beginning of the workflow, how you design a model for your task, how are you design a model for the different hardware to be able to really maximize the potential of tinyML. I think there is still a lot of things we can do on the edge without, to be limited on the basic tasks. I think by leveraging the advancement, the fast advancement of ML in the past few years, there are actually a lot more use cases that we can explore. And by focusing on the algorithm itself and how the algorithm interact with the hardware, I think is a way that we can tackle this problem together by exploring more and more potentials of the hardware.
Awesome. Yeah, I think that's exploring the potential of the hardware. That's the exciting thing with all these edge devices, right?
Yeah. Yeah.
Okay. Sorry, now on you. The model searcher tool in Nespresso suite of services finds optimized model architectures kind of aware of the inference results on each device. Can you describe that benefit?
Yeah. The problem we point out here is that there are so many edge devices, and there's even with the same edge devices, we have the very diverse number of runtime engine versions. So there is one benefit of awareing inference result on each edge device. In most cases, if you wish to attain a tiny DA model, it means the model will run on an edge devices which has different environment on which the model is trained. Usually model is trained on server scale, large machines with many GPUs, and then after it trained, it will be ported into tiny devices. That's the sequence. But then what if it doesn't work, or what if it's just slow? Then you come back to the server side machine and retrain, or we do some other things in the server side machine and re-implement it into the tiny device. So it's like a little bit cumbersome. So then tinyML could run well in servers, but it often fails to perform smoothly in tiny devices. That's the problem. So we have so-called device farm. Device farm, which has like a cat tower, like a big cat tower. So a room is we have a server room with full of servlets, and the servlet is fully filled with the different edge devices, and even the same device, we have different runtime engines. So there are thousands of edge devices in our server room. So once the candidate model is searched by our model searcher, it sends the model to device farm in parallel and measure the inference speed for each device at the same time in parallel. So the inference result will be immediately reflected on as a hyperparameter of the architecture search process of the model searcher. So if you use model searcher, which is one of our sub-service of a Nespresso, you will see the search model is already tested on real edge device even in training time. So then it means it's guaranteed for search and model to perform well in the tiny target device, since the inference speed is measured in real device or training time, and not after it's already been trained. So the model search will it doesn't mean a simulation or guessing the prediction result. It's a real device inference speed metric. The result will be implemented and after it's measured. So the point is the model searcher, there's no gap. There's no gap on model performance. It's guaranteed between server scale machine and inference speed in tiny scale machines. So do you get my point?
Yep, very cool.
Yeah.
So yeah, you're getting the real actual speed on the device as you're doing the searching.
Yes.
Nice. Cool. Okay, Daniele, how does QKeras and Vizier, Auto QKeras It's one of those two names. Work together to improve the tinyML process?
Yeah, for sure. So QKeras, Vizier, and AutoQKeras, they're all used for in the two phases, in the modeling and the training part of the tinyML process. So QKeras, of course, allows you to build models, right? It's a drop-in replacement wrapping around Keras, where you can just add a Q in front of any layer, and then it becomes quantized. So you can essentially do this in a very easy way, where you can iteratively create quantized layers and alter them to whatever application you need. So QKeras then helps you in the training phase with the quantization-aware training. So quantization-aware training has been shown in several places, including that CERN QKeras paper that I mentioned. It's been shown that quantization-aware training usually outperforms post-training quantization when you go to a low enough bit width. So in that regard, if you are looking at going below 8 bits, for example, QKeras can give you some pretty compelling improvements in your model accuracy. So that's QKeras. Then AutoQKeras and Vizier. So I'll just quickly clarify what the difference there is. AutoQKeras comes prepackaged into QKeras. So it makes it really easy to search all these different quantization parameters for whatever application you have. But it doesn't parallelize to, say, hundreds of workers simultaneously, right? You have to run each training, each trial, one after the other. Which is usually perfectly fine, right? But if you're trying to scale up, then you can go to something like Vizier, which also has some similar Bayesian search algorithms and a few other more novel search algorithms that can be applied to, say, hundreds of workers running on Google Cloud at the same time. So that can really speed up what your development process. So yeah, both of these tools can be used in this iterative loop of modeling and training, where you try some different architecture, try some different quantizers. You can also try different input pre-processing steps, right? That's all part of any number that you're writing down as a constant, you can make that searchable, throughout the whole process. So yeah, I think that can be quite helpful. I did also want to mention one more thing in the deployment phase. So with QKeras, once you have that model that you've iterated upon, right, you can use tools like high-level HLS for ML, right, high-level synthesis for ML, to convert that model to deploy on an FPGA or even a custom ASIC. And this is a very highly optimized application-specific machine learning. So you can, in this case, add more constraints to the type of model you can run, right? It has to be very quantized, etc. But you get, orders of magnitude of improvements in latency and power. Same thing as in the paper I mentioned. So yeah, although the deployment phase isn't part of QKeras and Vizier necessarily, it very well integrates into high-level synthesis technology.
Yeah, that's definitely an extreme version of deployment when you're talking about either downloading your model onto an FPGA or building custom silicon with the model in there. That is definitely deployment. I will ask a question from the Q&A. Alexander asked, can QKeras do less than 8-bit quantization?
For sure, that's what it was really made for. Not only can it go less than 8 bits, so you can choose the number of bits. You can say I want 1, 2, 3, 4, 5, 6. 9, whatever, right? Any number of bits you want, it can do. Of course, this has impacts on deployment, but that's another topic. And in addition to any number precision bit width, you can also do heterogeneous quantization. So let's say your input layer, well, you need to preserve precision because you need to preserve, for example, the fine differences in an input image, right? You don't want to lose too much, detail there. So the input layer can be, say, 12 bits, right? Then the next layer, okay, maybe it finds the more important features. You can go down to 4 bits, right? The next layer could be binary. You go back and forth. So that's really effective because then you can compress the layers that can be compressed, and you can keep in high precision the layers that need it. So you kind of get, the best of both worlds.
Awesome, thanks. I will leave the question open in the Q&A so you can send them a pointer or something like that, and it'll actually work. I think you couldn't answer before because I had marked it as answer live, so I won't do that this time.
Oh, no worries. Sounds good. Thanks.
Okay, Martin. So GreenWave's technology, as we were just talking about turning machine learning models into silicon. GreenWave's technology is a fabless semiconductor startup. So GapFlow helps optimize the performance of the neural networks on GAP processors. How important is it to use processor-specific optimizers for on-device performance?
I think this is a really good question. It's a kind of crucial question in this panel, actually, because it actually comes more to a question of where is the interface between the two? Where is the interface between, say, a QKeras or an AIMET or wherever, and something like a GAP processor? And that's really what we're trying to achieve with GapFlow. It's definitely true that when we design hardware, we don't design hardware thinking nothing about the software. In fact, we spend all of our time thinking about the interface between the software and the hardware, and where it makes sense to do something in hardware, where it doesn't make sense to do something in hardware. So it's definitely not, developed in a vacuum. And GAP9 has a number of things in it which are, specifically architected for tinyML, from, the way that its memory architecture is architected, from the fact that it has, a cluster, a 9-core cluster in it, the fact that it has that cluster tied to a, convolution ML accelerator that can handle some of this, sub-byte quantization. The fact that it has, tensor compression in it or decompression in it, the fact that there's a whole load of other, even further, smaller, detailed trade-offs which are in there. And for us to be able to exploit those, I think it's very important that we have a certain amount of control over some of the tools. But the question is then, how do we exploit make the most of all of these marvelous tools which are out there? And really what we're trying to do there is to provide an interface to those tools, a good boundary that allows those different tools to be used with our tools, and having a high level API that can drive our stuff and actually give the benefit back to these other platforms that, and you were mentioning earlier that being able to actually get physical data back from running on hardware. Well, we can, through a Python API, go down to the point of running that model on the hardware, extracting back not only the performance data, but also the tensors which happened there, so we can check the accuracy and check that the results were the same. And then also pull back even more detailed information about, memory performance, bottlenecks and so on and so forth, even down to, profiling tools. So I think as we move towards processors which are more and more specialized, and there's a number of them out there, having the companies that are making those processors do a certain amount of the tools to a certain boundary is going to be super important. And I think we see that even with GPUs now.
Yep, that's a really good point, and we see that with all the different libraries that are out there for the different GPUs, and all the different even acceleration libraries for different embedded processor architectures that people adopt, and the tool chains keep getting more complicated. So yeah, I think like you said, defining those right interfaces and the right place to hand off is kind of critical. Awesome. Chris, why do you think it's important for a tinyML, AutoML tool to assist with more than just the machine learning, modeling, and code generation? Nope, Chris, you're still on mute. Hey, we're all doing really good if that's the first time I did that in the last hour and a half, so be happy.
Let me switch microphones. Can you hear me now?
Yeah, we can hear you now.
For some reason, my other one went kaput in Zoom. So as I was attempting to say, I think Kiel had a great slide where he had a quote from a data scientist that said that the problem with analytics and AI has nothing to do with analytics and AI. I think there's been sort of a well-documented thing where even in cloud machine learning and AI, where data scientists end up spending 80% of their time not doing data analytics, but in the other tasks in the workflow of data cleansing, pre-processing, labeling, organizing the data, fairly mundane things, right? We've seen that over the years. We've had customers in the early stages before we had tools to help automate the process where customers were using Excel to do their labeling and writing custom scripts and sort of managing all the data files. If you compare that to like more mature development tools, they have IDEs where you combine profiler and debugger and code writing and editing tools and version management within an overall environment. I think you have to look at AutoML as just one aspect of what we can really help automate in the overall workflow that users have in building tinyML models. And so we built a companion part of our tool suite called Data Capture Lab, which helps automate some of that mundane aspect, but very vital portion of curating the supervised machine learning data sets used for train and test. So eliminating the need to write custom scripts and figure out file formats and how am I going to put labeling conventions? Am I going to do that in the file name? We do it all within a database approach. So we can import data sets in from other existing data that you have. We can export out all of the knowledge that you put into your data set using our tool, so you're not sort of held captive. We believe that customers should own their data. So while we put all this value into it through the Data Capture Lab, you should have the ability to get that out of the tool and not be captive within ours. So we have a fully defined file format that lets you export out and use that in whatever tool you wish. But obviously, if we're doing our job well, we're continuing to innovate and building out more automation to address some of these other facts that I need to have ways to address version control from the people that are doing the labeling, right? Individual domain experts that are labeling bring their own personal bias into the problem. So understanding who did the labeling, be able to maintain multiple sessions of labeling, and simply manage the files better helps with that 80% of time that people are spent just in the curation of train and test data sets.
Just something to add here to Chris. I think it's a really interesting kind of aspect that he touches on, which is like in the end, automation of this kind of stuff. Like I have new data coming in and I want to go and label that whenever I'm unsure of something that happens, or if I know that something is happening in the field, I want to push it back to my test bed and tag that. It's super important. No one gets their data set right the first time. And if you have that flow, sort of an active learning loop, my ML team likes to call it, but then all of a sudden it's not a one-off that you're building, and making those improvements over time is, I think, super valuable. So glad to hear that tinyML is thinking along those lines as well.
Yep, agree completely. And I think that leads pretty well into my next question to Magnus, as far as how real-time data streams fit into the tinyML development process.
Yeah, that's a good question, really. The thing is that with streaming analytics, the whole process becomes a bit different. I mean, it's very efficient to work with streams. I mean, many of us are talking about the need of seeing data, about learning about the data, about cleaning the data. And there are problems with collecting the data, then finding out you didn't cover all the corner cases and stuff like that. But if you have access to live, like real-time data, it gives you like new opportunities to understand and to see and to analyze the data instantly, which will help you immensely when building models and giving like insights into the problem domain. And I mean, when we talk about streaming, I mean, sensors, they inherently provide streams, but with a streaming platform, you can, instead of just recording and then doing all the processing and insights offline, you can interact with the data live in real time and get this sense of insights from the sort of real time and real world environments, and that's pretty profound and sort of affects the model development process quite a bit. And for example, for in our platform, we don't have the need for firmware updates. So many of our customers, they work directly on real world environments to sort of already in the sort of data realization and visualization process before starting to develop models, and they basically have easier access to real world data and to sort of get insights into the corner cases and things like that. And if you look at the development process in summary, you can start out by just looking at the streams and interactively transform them and refine them and filter them and just clean the data to get exactly the data that you need. And with this interactivity comes the insights from the sensor data streams, and then you can start applying models to the real-time streams and sort of play around, and when you're satisfied, you can deploy the models to the edge devices to sort of test them in real world environments instantly. And since you don't have the need for firmware updates, it's quite an easy interactive process. And also you see the results immediately, so you get the insights, and then from the insights you can sort of refine it again and do some tweaks and iterate and redeploy, and sort of you get a more hands-on work with the live streams, really. And this is especially important in we work a lot with large industrial companies, for example, in the automotive industry, and they have quite complex environments, and it's seldom that one model sort of fits all their cases, and you maybe even have to apply combinations of models, and this the insight and the end result, you have to sort of build it iteratively and with a lot of interaction going back and forth. And for example, if you see a model that is sort of experience model drift, and then you can sort of hook into that and try to transform it and examine to get the insights that you need in order to either retrain the model or maybe adjust the input streams to sort of adapt more to the original sort of format of the data that your model was trained on. So it's a lot about sort of interactively getting the insights to better aid the model development and going quicker and getting the better output in the end, really. So there's been a lot of focus on quantizing and optimization of models, and that's really cool. And we can see this sort of as a complement by adding the ease of deployment and orchestration to these optimized models. For example, we have some support for quantized TensorFlow-like models, and we're working a bit with OpenVINO support, for example, for optimizing for Intel devices and things like that. So yeah, so that's sort of a complement that simplifies the whole process of working with the insights and the model development, really. And for the AutoML part of it, is like, since it's a platform that also can communicate with servers, and it sort of facilitates things like federated learning and things like that. So that's sort of tying into the AutoML part of the development process as well. So yeah, so that's really the key elements to the pros of working with real-time data streams in tinyML.
Very cool. And just because you mentioned federated learning and maybe some on-device learning, I'll throw a shout out to my another fellow working group that will have a bunch of Zoom sessions at the end of the summer. Look for those on tinyml.org on exactly that topic. But and I just wanted to somebody Pan Wang just asked a good question that was along the lines of the answer, Magnus, that you just gave, where he said, and Dee, thanks for putting an answer on there, but I thought I'd throw it open to everybody on here. He said, as we know, pruning, quantization, and distillation are crucial in model compression, for tinyML. And I think Magnus mentioned, kind of deployment and some other things like that. I'm paraphrasing the question, but what are other crucial technologies for AutoML and tinyML deployment? Does anybody want to take a off-the-cuff shot at that question?
Well, you mentioned one of them, Elias, which I think is the on-device training can help in certain cases. I mean, it won't help everywhere, but I think it can help in certain cases of actually training, maybe even, and this is a little bit more provocative, but training every time you do an inference, actually retraining to the environment that you're in is an interesting idea.
It's a really interesting thought. I mean, I'm really fascinated by this idea, right? So like so I think a lot of the questions that we try to answer, even if you're running classification problems, right, it's not even like, am I looking at X or at fault state Y or whatever, but like, is what I'm looking at normal, yes or no, or is there something weird going on? And this whole idea of like, can the device itself establish what is normal based on previous modes of operation, I think is super cool. I don't know the answer to it, but I think it's really interesting.
Yeah, I think we spend a lot of time in training on augmentation as well, which is always around kind of trying to adapt to all of these different environments that we're trying to think of that could be happening. Well, if you know what the steady state environment that you're in is, then perhaps there's no point in doing that and train to the environment that you're in at the moment. But obviously it's a challenge, and there's challenges in doing that. But it's it needs specialized architectures to do it. I think we believe that it does.
So one of the really interesting, maybe a counterexample, maybe we don't need this. It becomes really roundtable now instead of just opinion. But so here's an idea that I've had, and I've been prototyping a little bit on. It's not productized or anything, but let's say we have a classifier, right, to detect whatever you want to detect. Maybe let's say a vision-based classifier, right? I see my piano or I see a person. Now, what if we take the embedding just before the classification and we throw that through whatever clustering algorithm, and that's how we determine baseline. And now in something completely, and that's something we continuously keep building, right? K-means is something that can run really efficiently even on an MCU.
Sure.
What if that becomes just a baseline for that device, and we continuously keep improving on that until all of a sudden something that is so different than what we normally see that we say, okay, neural network, I don't trust anymore. This is like, I don't know what the hell is happening here. Let's throw this into a completely new case. Like this kind of stuff is based on stuff that we already have. It's probably stuff that you already execute, right? You already run this whole neural network through. Maybe it's something like that. I think it's really interesting.
Yeah, that kind of idea of instrumenting the last layer is it's not something that hasn't been used.
Yeah,
I mean it has been used.
You can basically do it almost for free, which is kind of cool. Yeah,
but I think we see those kind of use cases, especially with the on-device learning, personalization. Like they're becoming more and more prominent as we go. And the tinyML devices will become more smarter. Some sort of on-device learning, all those things will have to be brought in at some point. So
yeah. I think the technology that enables tiny devices to perform training, it already exists. We have some demonstration of that, running visual object detections on the fly, training, classifier on the fly, even on microcontrollers. Sure. I think resonating with Yang's points is that I think the challenge what we see is that how do we use that in the field? How do we make sure that a model just optimizes itself into another like a local optimal or other situations? How do we control that? Right? How do we interact with the user? I think that's where we need to resolve. Yeah.
Anyone else have key technologies that they want to bring up now?
I have two quick thoughts. One is the idea of hardware-software co-design. So if you look at kind of like the history of hardware development, it always, or at least, if you look at the new TPUs, they try to see what the current state of ML is, right? State of the art research, and then try to see how they can create hardware to run those models optimally. But you can see this is kind of, in some ways, a one-way street. If this was an iterative loop, we could design software and hardware, models and the hardware they run on simultaneously. So now we can try to come up with very novel ideas for models, such as I've seen a paper on logic nets, which uses lookup tables, for example, or very novel types of model architectures like, I don't know, squeeze and excite layer, stuff like that. And we can then iteratively design the hardware to also support that, right? Or also change the model architecture to support what's very efficient in hardware, right? Like in QKRS, we have a power of two scale where we do a shift instead of a multiplication for our quantization scales. So I think that's very interesting. And the other thing I've been interested in is this idea of a weight sharing neural architecture search. This is the idea is that instead of treating a search of the model as a black box, we can actually open it up. And we can use, there's a very influential paper called Proxyless NAS, which can basically allow you to train multiple different types of models, in the AutoML space, but they all share the weights. So the search is much more efficient in that way. So just bring that up.
Yeah, thank you, Daniel, for mentioning our co-founder Song Han's work.
It's great paper.
It is. Okay. Now we're getting a little bit behind, but that's okay. I'm going to move on to another topic that was also just mentioned in the QA, but go to Leslie from Kixo. Leslie, Kixo's AutoML talks about being a no-code platform. How much of the tinyML development process is covered by that?
Thank you, Elias. So users can go from concept to a working prototype without writing any code using Kixo's AutoML. Specific steps that are particularly heavy lifting code-wise that we can take care of include, we'll automatically generate data collection binaries for our supported hardware to collect sensor data. The usual kind of automatic ML pipeline can get executed, including various optimization steps, sort of for selecting sensors or features or inference settings, and then hyperparameter optimization. After training the final model, Kixo AutoML will compile the ML model into a binary to be flashed to the device, and then we'll interact with the device for live testing. So all of these steps, which would require embedded engineers, a significant amount of time to interface with the device, and ML engineers to build a pipeline, do all that, stitching it together, making choices and research, is performed without any code on the part of the user. Only if the user wants to integrate the ML model into their own firmware would they need to do any code level integration with the trained model. To support users in this task, we provide for download a static library containing the ML model for the user to link against their projects.
Awesome. Thanks. Okay, so that is all my questions on the kind of process section of the Q&A. I'm going to take a minute to remind everybody of kind of the overall state of the tinyML AutoML document that we put up there on that tinyml.org. If anybody joined us late, I showed it, and there are links to it if you scroll up in the chat there. But it's available on tinyml.org, and it's really putting together a bunch of very short summaries from each of our panelists on what their tools can do. They all include links to the tools. They have a lot more detail. Almost all of my questions are, kind of drawn from those as far as trying to, pull out some of the interesting facts there. But if you want to get a lot more of the background and the links, I definitely encourage you go look at the one-pagers, follow up with some of the information. And also, as we mentioned before, and again, there are links available on tinyml.org. There are going to be a series of deep dive sessions for people who want to follow up and learn more about the individual tools. A lot of the one-pagers have links to past either demos or deep dives into these tools and libraries that you can find on YouTube or other platforms, or going to the web pages, try the tools out, all that kind of stuff. But all that's on there. I really encourage you to go take a look and learn some more about any of the tools that have kind of grabbed your interest as we've been talking about things. So our last topic is on productivity. Really the goal here is to really make our customers, our users more productive with these auto machine learning tools. AutoML is always usually around improving productivity. Jan, you get the first one here, assuming you're still there. There you go. So what are some unexpected ways Eon Tuner impacted end customer productivity?
Yeah, so I put it in the one pager as well. So people see us as an ML platform. I think there's lots of other companies here that kind of fall into the same category. But are we really? I mean, in all fairness, we're in the business of getting customers to get insight in the data in real time on real devices. So for me, the most interesting one, which was done partly by using Eon Tuner, our Automl pipeline, and the rest by just manually looking at stuff, is that we had a customer that was using a deep neural network to do sleep stage detection. That after a bunch of feature engineering using the tuner, actually realized that they don't even need any deep learning anymore. So we found in total 57 features, out of which we actually used 20 of them. So we even cut it down further. And after that, could just use a random forest classifier to go use the classification part on that. And that is infinitely better. And speaking as an embedded engineer, it's infinitely better than a deep neural network, because now it can actually see exactly what is happening at every stage and debug that. And that is really important. So this actual product, this model went into in a consumer product that shipped over 1 million units. Explainability and debugability of that is really good. So it sounds stupid or weird, not stupid, but it sounds weird as an ML company. But the less ML, the better, at least here, and this definitely helps with that.
Yep. We definitely see a lot of the same thing. A lot of times the simpler we can make the models and the easier to explain they are, that ends up helping the user in a lot of extra ways. Sam, what are some of the ways ImagineMob AI improves productivity?
Yeah, so we built our platform with the idea that it should be easy to use, and it should be able to easily integrate with different sensors and deploy on any kind of tinyML device. Those are the target goals that we went going in, and that we try to aim for when we build the platform. And we built it on top of our own usage of it. So we were using the platform to develop applications for customers. So it's heavily based on our experience with what we found working for different applications. You can break it up into 4 parts. So that's ImagineMob AI improves productivity. The first one is data management. And there, the number one issue that we've dealt with is something that Shell pointed out, and that we we realized that's very crucial, which is the data annotation. So one critical feature that we have is to be able to have video data or accompanying metadata to be used for the annotation process alongside your time series signals. And this allows you to essentially understand what problem you are trying to solve. How does the sensor output actually look like under different conditions and scenarios, which allows you to get a better understanding of what issues your model might also face. So that's the big one. And then as part of that, this is the visualization aspect, but we've also, for example, had issues with the customers having the wrong sampling frequency on different data sets, which can lead to problems with the model, where some of your data is at 3 Hertz and the rest of the data is at 30 Hertz. It can make a significant impact. So that kind of data quality checking functionality we have in there. Another application is some of our users had like some of their data sets had five features or sensor signals, and another one had like 7. So when they would try to create models, it would create problems, and they couldn't figure out why, because they hadn't actually opened up the data files and looked closely into them. So this, all of these things we try to encompass in the platform for the data management aspect, and this can save you weeks of fiddling around trying to figure out what the hell is wrong with your data. Where it's just something very simple, you realize, oh, I accidentally turned on one of the sensor signals that I don't actually need. The second part of ImageMob AI is the AutoML functionality, to be able to generate different kinds of models and to actually visualize their output alongside all of your input videos and data signals and things like that. So you get a deeper understanding of where your model might have false positives or false negatives. You can take a look at the data for those signals and see how you can supplement it with more data, for example, or do some extra, add some pre-processing that might highlight those differences to improve the model performance. That's the second aspect. The third one is about deployment. And in that regard, we try to make it as simple as possible for the model to be converted to an edge compatible model. So we convert our TensorFlow models into C99 source code, and it's a single source file with only 3 API functions. So the idea is that it's very easy to just take the model and put it on the edge. Anyone can do it. And then lastly, which is I think a big hurdle for customers and users, is the integration with sensors. So you have many different kinds of sensors out there, and some of them are extremely difficult to get data out of them. So we strive to try to integrate sensors and boards so that it becomes very easy. So you can essentially plug and play a radar or an IMU and get data from it. And to also be able to deploy models on those same boards. So,
excellent.
Yeah.
Great. Thanks, Sam. Yeah, and I mean, I think you kind of described a lot of the different ways. You know, it is often more than just the model itself, right? And so, Dee, can you explain what it means to make a machine learning model deployable from the start?
Yeah, certainly. I think one of the biggest productivity issue that in this whole tinyML model development process is this long iterations, right? These dependencies. There's a ML team or data science team that trains a model and then get a certain accuracy. And typically there is a hardware team, right, that optimize the model, quantize the model, compile the model for deployment. And usually what happens is that, once we get a model and incorporate some of the state-of-the-art techniques and the state-of-the-art advancements, and then tune for the internal data sets, the model may not directly be workable on the hardware. It could be, containing some operators that are not supported for example, by some vendor SDKs. It may not contain some layers that are extremely inefficient. And then, so the hardware team will provide all of these, insights back to the model designer, and then you have to redesign the model. You have to fit a model better for that. So there's a lot of manual iterations, manual communications between the two teams. We've seen this in large companies. Also, we've seen this in companies, customers that are doing, early prototyping. So with that, you prolong the time to market, prolong the production, prolong the prototyping sessions. And at OmniML, we believe the best way to solve that manual iteration is by empowering the ML engineer in the design phase to automatically consider all of these hardware constraints, and then empower them to do all of these experiments, not at the deployment stage, but at the model design stage, right? Through neural architecture search, through hardware-aware feedback loops, we are able to help ML engineers explore all kinds of design decisions, whether to use list layers or that layers, what resolution you want to use, and what types of configurations for your network. Do you use 3x3, 4x4? Do you use a lot of depth-wise convolution layers? What channel sizes you choose? All of that decisions can be made by an automated neural architecture search optimization flow. And then a lot of that can also be done without the need to retrain the model, right? So that's the power of the we-sharing NAS that Daniel just mentioned. You train a large network once, and then you can actually customize that. You can sample that large network, targeting different types of hardware constraints, right? Once you train the model, you want a model that can run 30 milliseconds on this Raspberry Pi device. And then you can evaluate the accuracy. And if the accuracy is not enough, you can relax the constraint. You can say, I want a 50 millisecond model that runs on the Raspberry Pi. And then you don't need to retrain, right? So we give you the model that runs 50 milliseconds, and then you can evaluate the accuracy. So by keeping the experiment, keeping all of the exploration in the model design part, I think that's a fundamental change in the development flow, and then that will boost productivity significantly.
Great, thank you.
I have a follow-up question.
Go ahead, Daniela.
Yeah, I think this kind of technology is really, I think this is the key to the future of tinyML. But one question I have for you, so you talked about latency, right? Are you also looking at other metrics of cost? And how do you handle that, especially when it might be tricky to estimate the cost in hardware?
Yeah, I think that's a great question. What we provide is a set of constraint APIs. So the constraints are programmable. The user can define different types of constraints, right? In form of latency, in the form of max or model activation sizes. So right now it's sort of like it's almost it's a weird analogy, like an ADAS, right? So you don't fully autonomously make all of these decisions exploring this complex cost metric, because each customer may have their different cost metrics and they know that best. What we provide is a set of assistants, right? Like you can explore different ways to configure the model easily without retraining. And then the customer himself can establish like energy constraint, right? The energy constraint can be somewhat translated into a combination of latency versus the size of the model, stuff like that, right? Or another use case is that some customers may choose you need to run multiple models on the same device, right? You may run some models on the GPU, you might run some model on the DSP, for example, on the SoC. And that, those kind of explorations are easier if you don't need to explore, if you don't need to couple that with the training process.
Mm-hmm. Yeah. Very cool. Thanks.
Thanks for the question.
Cool. Thanks. Okay, Martin, gap flow can be used inside a continuous integration process. How does that impact overall development productivity?
this actually kind of follows on really nicely from what Dee was saying there, because I mean, fundamentally, what we're trying to be is, to a certain extent, the feedback loop, and allow people to create this kind of, I often think a CI is kind of like the collected intelligence of kind of, the evolution of your product. All of these tests basically say, this is what we understood, this is what we've learned about what we're trying to solve, because fundamentally the tests are the specification in a lot of ways. What we try and do is with Gapflow is give people the ability to, at different stages of going on to Gap processors, be able to get an idea of, has what I've done or changed affected accuracy? Has it affected the way that the model is running? Has it affected the overall structure? And give good feedback in terms of where that happened. Because, you can make a very small change to what you're actually giving a tool chain to produce a running model. Our tool chain goes through lots of steps to produce that running model. And you can make a very small change and get some results which are really surprisingly different, in terms of performance, definitely. The slight changes in terms of quantization will make big differences in ways that probably most programmers and most people developing would not anticipate, because they don't know the intricacies of what they're developing for. And I would say that's actually even true on classic processors. It's just that people don't optimize at that level, right? But if you're writing, a DSP filter for a classic processor architecture, and you look at the code of people who have written those who actually know what they're doing, you'll see that they exploit things which you wouldn't know as a normal programmer anything about in terms of how to exploit that architecture. So what we try and do with the tools is give a way that you can plug into your test process. Okay, I want to now test at an accuracy level. I want to now test all the way to the device. And also these things can be used as feedback mechanisms into, exploration techniques used by some of these platforms to actually explore the space and see how you can get a better result. So that's what we're trying to do.
Excellent. Yep, makes a lot of sense. Blair, can you describe how Newton tinyML improves the user's productivity?
Yeah, I can try my best. So I guess when you begin to think about productivity, is at least for ourselves, we think about it in the context of enablement and empowerment. And then I would also say, and this is always just a little bit of a joke for myself, what is a model that's not implemented? It's just a shiny object, right? That's it. No more, no less. So when it comes to productivity, for us, we really want to make sure that we're enabling our customers, our partners, to reach production. Other than that, it's a fancy exercise. And in reality, there's not that many data scientists that are out there that can help empower organizations to achieve their goals. So our objective is, as I mentioned in one of my previous answers, is, how can we bring machine learning to everyone? And to me, that's what productivity is all about, is enabling and empowering everyone so that they can achieve their goals. Because why else are we here? So when you begin to think about productivity, at least for myself, I began to think about what are those headwinds that are preventing organizations, that are preventing our partners, our customers from achieving that goal so that they can take advantage of this technology. And like many of my other colleagues on this call, number one is you want to have a solution that enables everyone to be able to take advantage of the technology. In this case, we say AutoML, right? We say we want to have a zero code solution. We say we want to have a solution that doesn't require any expertise from a data science perspective, right? Because we want to enable and empower the masses, right? It doesn't mean that we're ignoring everyone else, because I still need a mechanic as it relates to my car if it breaks down. But in reality, I just want a car to drive from point A to point B to help achieve my goals. And so for us, when we talk about productivity, we're trying to accelerate and enable the time to market. We also are trying to reduce some of those headwinds that oftentimes exist, right? That iterative process as relates to, let's say, building a model. And then we want to also make sure that in accomplishing our mission of making machine learning available to everyone, we want to make sure that we build models that can be embedded or integrated into any device. And once again, what's the most significant currency when it comes to tinyML? It's space, right? It's consumption of power. And we want to be able to enable our customers to be able to produce the smallest models possible, and not compromise on, of course, in this particular case, accuracy. And then lastly, we want to enable the community. So we want to enable the community to be able to take advantage of our platform, take advantage of being able to, build and produce models that they can implement on whatever experiments, whatever hypotheses that they're looking to accomplish. So I think, for me, when it comes to productivity, you want to be able to check all of the various boxes from a technical perspective, from a usability perspective, from a time to market perspective, and of course, accessibility. So what good is a product or a solution if everyone can't take advantage of it? And that's one of the reasons why we make our platform available for free. So that's my definition of productivity, is being able to check all of those various boxes.
Yep, makes a lot of sense. Thanks, Blair.
All right.
So pretty much the same question to you, Leslie. For Kixo AutoML, what's the impact on customer productivity?
Thank you, Elias. Right. So we have many customers using AutoML every day to collect new data, train new models, to iterate, to deploy, test. It is difficult to estimate the actual amount of productivity improvement because for some of these customers, they don't have any ML or embedded expertise at all. So they don't have any engineers. The tasks that they're performing wouldn't be possible without a tool like Kixo AutoML. Maybe getting more specific, I think a tool like Kixo AutoML can give productivity improvements in two major ways. One is if a customer has a solution already or has built up a solution to a prototype level, and they want to commercialize it. And they want to commercialize it in different environments. So in the keynote, Kjell talked about how in practice, the different environments might have different data associated with that. And you've solved the problem in the lab or for one environment, it works well, but you need to make sure it works for the arid soil or the moist soil or whatever. This is an experience that we definitely had at Kixo when we were developing our own ML applications. So we've got a product and we want to commercialize it to a specific scenario. Without a tool like AutoML, that might take a couple of engineers a week or more to collect some sample new data, convert the model to work in the new environment, and then deploy. With Kixo AutoML, that might take one non-machine learning engineer an hour or more to collect a little bit of data, retrain, and deploy. It's this kind of tool that allows customers to scale, to produce commercial products in a way that makes sense for them, that is profitable for them. We found it ourselves as well when we were doing our own applications. The other case is a little more speculative, which is a customer has an idea for a solution, but they don't have the solution yet. They don't know how it's actually going to work. So a customer wants to solve question X. If they don't have a tool to do that, to help them, then they need a team of ML and embedded engineers to start from scratch, to go from what sensors do we need, what platform do we want, what data do we need to collect, all the way up through prototyping. That means writing embedded code to collect data and also to wrap the model and do live inference. That means building up that ML pipeline or something like it to make all those decisions and do all that research to extract features, etc. With Kixo AutoML, a lot of that stuff is done for the engineering team. So even if that engineering team has ML and embedded engineers, being able to start up from scratch using a tool like Kixo AutoML can save a huge amount of time. It's the kind of tool that we wanted to have when we were doing our own applications, which led us to create this kind of pipeline for ourselves to spin up new products. Hard to estimate. I think it's possible that it could save months of time, literally, having that head start.
Excellent. Thanks, Leslie. Okay, last but not least, for sure, Magnus. Can you give us, and Magnus, can you give us an example of how Stream Analyze can complete an edge AI iteration in minutes?
Yeah, sure. This really ties into how the process becomes a bit different and very efficient when working with data, streaming data as the foundation. You get this, as I mentioned before, a bit of increased productivity. And so with all of these steps, which are part of the analytics cycle, becomes a bit easier to manage, I would say. Like the getting insights by like refining and filtering data streams to sort of get exactly the data you need, and then to apply models to the real-time streams and also deploy the models to the edge devices to test in real-world environments instantly by bypassing the need for firmware updates, and that's really the key. And you see the results immediately, and then you iterate and redeploy. And when you get the hang of the cycle, you can really start to do this, get the process down into minutes sometimes. So that's really one of the strengths with having the streaming analytics platform for doing this analytics cycle. And the fundamental thing in this is really that the analytics cycle is separate from the software cycle. And so you have the sort of a total interactivity with the device. And our customers, we work a lot with, as I mentioned, the large industrial companies, and they work with this process today. And when you have a separate data science department and a separate embedded development department, and the data scientists, they usually need to sort of wait for the embedded developers to finish their software before there will be a firmware update where they can piggyback to get their models onto the device. And that process can take months, really, or even years. And when you separate the firmware process from the analytics process, then you can start doing this analytics cycle in a really short time span. And some customers have really given us the feedback that now it's down to minutes to do a cycle, and previously it took us months or even years. So that's a real breakthrough for them. And as I mentioned, especially in these large kind of industrial companies which have this sort of rigid setup. So and another part of the sort of productivity gain is also in the orchestration process. Like with this platform, you can sort of orchestrate by deploying to many devices, and since you're not limited by the firmware updates, it's easier to manage like thousands and hundreds of thousands of devices, and you're not having to address each single device by doing firmware updates for each new deployment of models and things like that. So that's really the major gain into productivity from working with streaming analytics, I would say.
Awesome. Thanks very much, Magnus. And that's kind of the end of our questions on productivity as well. And we're getting right to the end of our 3 hours, which is when on Zoom we all turn into pumpkins, right? That's our Zoom fatigue limit. So I'm gonna try and wrap us up here, I think. So panelists, ready for some questions? We're gonna get started right away here. So sorry to just again to remind everybody, as I've said a couple times before, a number of companies, a number of our panelists have signed up to do follow-on deep dive tutorials, kind of 1 hour tutorials through the tinyML webinars. You see the dates here. If you go to tinyml.org, in the AutoML forum event page, there's a link. We've also pasted the link a couple times into the chat here, to a page that has links to all these signups. We'll also keep updating that if other companies come in. We may also be updating our, sort of state of the industry document as if other companies come in and they say, hey, include us too. The whole goal here is to really give everybody a breadth view of everything that's going on in this obviously really exciting industry, because you saw all of our panelists today talking about a lot of the really interesting and exciting things that are going on. So with that, I'm going to start going through the very many sponsor pages, strategic partner pages for tinyML, while I also thank kind of all of our panelists today. I really appreciate everyone's time, the hard work everyone put into preparing for this event. Sam, Martin, Wanyu, Jan, Danilo, Magnus, Leslie, Dee, Blair, Shirag, and Christopher and Chris. Really great job, everybody. I think it really went well. I'm really happy with how it all turned out. And thanks also to the whole working group who helped me, who we all worked really closely together to put all this together. Thanks also to Gajel for our keynote there at the beginning. And of course, as thanks to the tinyML Foundation organization for, really helping all of us help this whole market come together. And of course, as I'm going through them, all of the sponsors of tinyml.org who make all of that possible. I think we're all kind of united in seeing the vision of this whole industry and all of the potential of it. And we hope that you learned a lot today and that you're excited by some of the tools you saw, maybe all the tools you saw, and want to learn more. Please do attend future events. There are discussion forums on tinyml.org. There is also, as I mentioned before, a number of documents and resources and follow-up sessions. So please stay in contact, reach out to any of us on the call here, or reach out to tinyml.org to learn more and follow up. And that is all for today. So thanks very much, everybody, and have a great day.